as a function of frequency is very different. So if you want to use LIGO is not sensitive enough. LISA may barely be sensitive enough, so you may have to go further. So to detect the gravitational wave coming from inflation. So the alternative way that we talk about is that there's fluctuation due to gravity, and the light, the microwave coming towards us will pass through them and induces the B mode polarization. And so the indirect way is to detect the microwave B mode as a way to probe the primordial fluctuation due to space-time. So that's again one step removed, but the chances of that is much better at the moment since we only have advanced LIGO, we don't have anything beyond that.
We know the magnitude of the energy density at the scale of inflation is much larger than what we observe today. Do you have any, would you like to offer your understanding about how this could be understood?
Yeah. So inflationary universe is very clean, solve a number of problems. But one thing is still we cannot pinpoint is the magnitude. So the magnitude can still differ by quite a lot. So one of the parameters to fit the Kobe spectrum is the magnitude. And so far, the inflationary scenario have many, many models, and they can have very different magnitudes. So it's really a paradigm instead of a concrete theory. So that's the still missing link.
The universe is expanding, accelerating. It's right, but the outside is what we don't know. Outside the universe is expanding without obstruction. You can sure there's no obstruction in the outside. Maybe something obstacle there and
right. Okay.
Right.
Okay. So that's a very good question. So anything we cannot think of a Gedanken experiment, experiment in principle to measure and test, then I would personally consider as philosophy. So our job is to convert something which like philosophical to find way to test it, so we change it to science. And hopefully one day somebody can measure and test it. What's outside our universe, we cannot measure. And as a result, it's not scientific. Of course, we can speculate, and I can assure you many, many speculations what is outside. You can hear about the multiverse or the universe outside, maybe the inflation bubble, great, expanding, many, many speculations. But almost all of them, with few exceptions, have no predictive power that we can one day hope to measure and test it. So that's a philosophical issue. And you may be right, whatever you say, cannot disagree. But most people believe that if our universe is inflate and then convert down, so probably outside more or less a huge region have the same property. And this also allows another speculation which is called eternal inflation, which means that somewhere outside is still inflating. Then the problem becomes much harder even from Einstein's point of view because the issue of measure and who's observing what become not true.
Maybe to the limit it contract to the...
So as far as the theory today, the universe is not going to contract. Although there are models that cyclic universe want to have it contract or go through cycles. But they always have
the bounce theory.
Yes, that's a bounce theory. The alternative to inflation is the bounce theory. But the bounce theory do not give us prediction like inflation. They give a prediction which is totally wrong, and then they can change the bounce theory to fit the data after doing something which is not clear as natural. And then that face some conceptual problems and So I'm not saying that they are wrong. What I want to say is that it's a very important effort to find alternatives, even it does not make very natural sense. But once you have an alternative, then you can say, alternative predict different things. They can focus more of the cosmologists and theorists to pinpoint where we can prove inflation to a high level. That's the way I look at it. So.
Okay, Bob.
Okay. Yeah.
Yes.
So I know the data, for example, the CMB data really fits the inflation theory very well. However, why inflation only happen once? If, from those energy density fluctuation, it seems can happen many times, not just once. And so, what actually stops the inflation after that 10 to the minus 35 seconds? And also, what kind of physics that really drives it?
Yes. Of course, once is the simplest, and there's no data which suggests that more than once have happened. Okay. Now, on the other hand, inflation is very strange. Whatever you have there, you go through inflation, all inflated away. So the past history before inflation is wiped out. You're just a clean slate. So if inflation happened before the one that we are measuring, all the thing would be wiped out by the latest inflation scenario, because they just inflate everything away by 10 to the 60, everything gone. You can have a lot of particles, and then you end up with only one particle per size unit. So if inflation happened multiple times, we can only see the last one, because the previous one, whatever signature there, you wipe out. So this is another very, very interesting point, is that you always say, whatever we do, we have to know the initial conditions. Initial condition will tell us what's today. And inflation essentially saying, I wipe out all the initial conditions, whatever you start with, and I replace by a simple new initial condition, which is nothing but target. So that's really a way to create a universe without having to rely on initial conditions. Now, to the second part of your question, it's possible that we're entering accelerating universe, we may be going over inflationary universe for the second time at a much lower rate, a much slower pace, but still inflationary in the sense that the universe is growing exponentially. So we're entering that stage now. What happened to that, nobody knows. How that will end, we don't know. So.
I know you're 10 to the minus 30 meters. What is that?
Oh, that's the size of the initial universe that grew to the apple size when inflation ended, and then go to our observable universe today.
Right, but that's a model. That's a what?
You just work backwards, that's the size. It can be 10 to 30 seconds. I'm not going to put all of you on a minute. In fact, the B mode measurement will put a bound on that value.
Yeah, in your beautiful story about cosmology, I mean, you're using a lot the dark energy or the cosmological constant, which I think is in the center of even the Higgs discovery. I mean, when we discovered the Higgs, the Higgs is a particle, but we know that we're basically proving that there is a field associated with it, which means a cosmological constant, right? That is huge.
Yes.
Yes. Why doesn't it gravitate? What, I mean, and how does this affect your story? Does it affect your story?
Okay, so the dark energy we measure today is very, very small. If you take a typical Higgs potential, and so say the Higgs potentiometer break, then you may get a dark energy which is much bigger, either positive or negative. Okay? So that goes down to the story of the puzzle, why the dark energy today is so very small. And that's still an open question. We don't know how to answer that. Okay? So that's as far as the inflationary universe goes, that's an input we put in today. I would say that the question why the cosmological constant of dark energy is so small today and not zero is probably the single most puzzling question in fundamental physics today.
Okay,
String theory may explain it, but that's a whole different story.
only students' questions now.
Oh, that's one back.
Last question.
Good afternoon, Professor. And I'm just curious about what's the physical meaning of the multiple moment, the peak in the multiple moment. Yeah.
So you're talking about this curve, right?
Mm-hmm.
So these are called acoustic peaks. So what happened is that the microwave or light is produced early universe. But there's a period of time where the universe is very hot. So the electron and the proton or the nucleus are not binding to atoms. So they are really freely moving. So that means that the microwave or light cannot pass through. It's opaque, the universe. So it's opaque, then they're trapped. And they were trapped. That's essentially like a form of resonance. Like if you trap something in the drum, that would be resonance. And these are called acoustic peaks. That's how it comes from. And then as the universe cools further, the electrons and the nucleus form atoms, form neutral, so then the light and microwave can pass through and reach us today. So from that point of view, this is a consequence of the fact that the cosmic microwave background radiation, of course, at that time they're high energy than today. They're trapped in this opaque medium. And so they don't travel, so they're standing wave, and standing wave oscillates typically, and these peaks are due to that. So we measure about like 9 or 10 peaks by now. You can see, okay, these peaks. And then they actually can go further down, beyond Planck, because on ground-based experiment, they can go to 5,000 nowadays, L. So, and the peaks are all predicted because the picture I described.
Okay, I think we stop the questions here, but you're welcome to come down and talk to Professor Tai. So let's thank Professor Tai once more.